65 minutes. Last time, what we did was we talked about a number of different notions of data models. We talked about the codicil or network data model, which Bachman originated, which meant that you had to navigate around and follow C-like pointers yourself. We talked about IBM's IMS hierarchical model, in which everything is arranged in trees. And we then talked about relational, which is what this class is mainly going to be about. But I would like to emphasize that old stuff never entirely disappears. The network model showed up in object databases, which were greatly in vogue about 20 years ago. And there are elements of the hierarchical model which show up in both XML and JSON, which are very much in use right now in databases in which, if we have cycles for it, we will be talking about at the end of the class. And the difference I mentioned briefly last time is that with XML and JSON, you have two things that are important differences. Number one, instead of having single values inside these things that look like cells of a matrix, you can have multiple values. For example, you could have not just one child, but a whole bunch of different children. Or if you had a team, you could have a whole bunch of team members as opposed to just one. Or you could have an address which is made up of different pieces as opposed to just being an address. So that's one of the big differences. The second is relational gets a fair amount of its power because you've got a schema, and that schema is fixed, which allows some things to be done very efficiently because everything that you have as data in the schema has to fit the rules of the road of that schema. And we'll be talking a lot more about what having rules of the road or constraints means in connection with database. And that's very powerful because you know what you've got. And it's very annoying because sometimes you want something that isn't part of the rules of what you have. You want to be able to have a new attribute describing your data, for example, that wasn't there before. Or you want to have a new value for an attribute that wasn't there before. And XML and JSON and protocol buffers and other sorts of variations of that semi-structured data allow you more freedom. So you get a lot of power for limitations. You also get a lot of limitations from limitations. That's how it works. By the way, I'm not using a microphone here in this classroom this size. That's never been a problem. Of course, people in the back row can always move up, but I don't think that there's going to be an issue with people hearing me. And as I mentioned last time, I'm not going to be webcasting this class, and I actually posted something on Piazza that explained why I like participation. I like to see the glazed looks on people's faces when they don't understand. I like to get answers to questions, and I love it when people really are understanding, and that gets reflected by answers. I tend to like to take votes on things to see what people think the answers are. So that really helps me teach a class where I really feel that there are students who are involved in the class, and I think that that's a good thing. So continuing on, there's a whole lot of data that isn't in database that's out there on the web. So it used to be that databases were used the way businesses ran things, and you had sensitive information, and you really cared about transactional properties. But there also are things that are less structured that are out there that we've already mentioned. Sensor data, keeping track of information from places where things are located, keeping crops, mechanical devices, robots, and so on, automated cars of various, or autonomous cars of various sorts, the web clicks that you do. All of that gets collected and analyzed and used to help sell you additional things. There's a huge amount that goes on. More and more of that data is stored in the cloud, and people keep track of how often you access your data in the cloud, all sorts of other things. There's a huge amount of stuff. Data has been described as the new gold or oil, as I mentioned last time. It's extremely valuable for figuring out how to sell to you and make money off what you do and what you see. So today, there are things that aren't in full databases, but it's sort of interesting. They're sometimes called NoSQL. And when NoSQL debuted as a term, it was spelled with a small o. And it meant, why do we need these stinking relational databases in the structured query language SQL? We can do all kinds of stuff ourselves with new sorts of systems, and we don't have to use SQL. You'll notice that when I wrote up there, there's a capital O. And the reason is that people like SQL and use SQL. They didn't have to. But a lot of people wanted it because so many people use SQL, and also SQL has a number of very strong properties that we'll be talking about. It's not perfect. I'll also make fun of some aspects of SQL as we go, but it has a whole lot of value, including the myriad of people who take courses like this and learn the language. So having abilities to work with SQL, that's great advantages. So they're referred to often as not only SQL systems. You can use them with SQL. You can also use them without SQL. And many of you may have heard of something called MapReduce that was first discussed by Google in a great paper by Dean and Gamelot. Hadoop was an open source system that was originated, that was intended in some ways to replicate what Google did with MapReduce. You also have the Spark project that originated at Berkeley that corresponded to the same sorts of capabilities. They started a company called Databricks to help support the use of Spark, which has a lot of advantages. There are things that are column stores. There are column store relational databases. There are also column store NoSQL systems. We'll be talking about things as if the data is stored in rows, row by row by row, a row of data, a record of data in a row. But data could also be stored, and I'll briefly allude to this later on. It can be stored in column form, not just in row form. There are databases that help you store with and play with graphs. There are databases where you store documents. There are all sorts of databases. Basically, anywhere there's a market, and somebody thinks that you can have a better approach than the standard relational products that are out there, somebody starts a startup company, and sometimes they make a lot of money out of it. So, you know, that's all stuff that's real. I mean, basically, the advantages of not having the full transactional capabilities that you have in most of the SQL systems we're talking about is that you can end up having easier ways of being able to scale and have larger amounts of data. Another advantage of these NoSQL systems is you don't have to pay the proprietary database system tax. Meaning proprietary systems tend to be expensive. That's what it means to be proprietary. You make money off them. And if you can use an open source system that's freely available, then you can take advantage of that and scale out without having to pay for the proprietary system. You don't get all the advantages of the proprietary system, but free is a whole lot cheaper than expensive. And some of the systems can be expensive. They don't have all the transactional properties, including, in some cases, consistency that you have in relational, but you do still keep a number of other properties as well. You don't have the full ACID support. You don't necessarily always have full SQL, but SQL is, as I said, being used more and more, which is why the little o, we don't need no stinking SQL, has changed to a capital, meaning it's not just SQL, it's not only SQL, there are other things as well. And now a short discussion on data and zeros. We're only going to be talking about the left-hand column over here. A terabyte, 10 to the 12th bytes. That's a million bytes. That's a lot of bytes. A person I mentioned last time, a fellow by the name of Jim Gray, whom I will be mentioning a number of times in this course, gave a talk on the order of around 15 years ago at this point about terabytes, spelled T-E-R-R-O-R, terror, not terabytes. Because it was kind of scary to think about having to manage a database system that had 10 to the 12th bytes. 10 to the 12th bytes these days is minor and routine. It's nothing. Kind of thing you have with one CPU. What you have instead are people who have petabyte, that's another 1,000, 10 to the 15th byte. Or in some cases, exabytes, right? That's a million bytes. And there even are things, I'll be talking about this on a later slide, with 10 to the 21st. And there was a rumor which I actually believe, but it hasn't been acknowledged, that there was an NSA database system in Utah. NSA is the U.S. National Security Agency, that had a yottabyte system. Million bytes. I hope they haven't bit off more bytes than they can chew, but they're all, I did mention bad jokes are us, we'll be all through the course. So, here you go. Another way of thinking about the amount of data is, a megabyte is a piece of music, a gigabyte would be a 2 or a film, terabyte, 6 billion books, petabyte seems pretty big, a stack of DVDs as tall as a 55-story British, spelled with an story building. And you get the idea, all the data that was generated up to the year 2003, that would be an exabyte. And all the data recorded in 2011, that was a zettabyte. And again, the rumor about this NSA center, which on this slide is being taken as true, they may very well be right, was, yottabytes. And by this time, if it was a yottabyte in 2013, who knows how big it is now. Data is out there and it's being stored and managed in various ways. There's a lot of stuff out there. Staying along with the theme, okay? Just how important is data? And this was as of, at this point, 2017. Hard to believe that was sort of 2 years ago, depending on which part of 2017. Volume of data worldwide across companies doubles. It's kind of Moore's law for data. Doubles every 1.2 years, a lot of different data. Having bad data can cost a huge amount, between a fifth and a third of operating revenue. Influx is putting a strain on IT infrastructures. Well, one of the reasons why cloud is very valuable out there is you can deal with the IT management by the cloud provider, so you trust security, but you deal with the cloud provider so that you don't have to have your own IT to handle the management of the IT systems. You still have software to deal with and so on. It doesn't entirely disagree, but you can take advantage of services and hardware that's out there in the cloud. A quarter of decision makers said that it'll rise. This was some years ago, that it would rise by more than 60% by the end of 2014, 42%. Again, 40% projected growth rate per year. And what's amusing is the amount of data goes up by 40%, but the cost of managing that data across global IT, in part because of cloud capabilities, is only going up by 5%. There are a lot of communities that end up being very happy when Amazon or Google or Facebook or whoever decides that they're going to put a large warehouse of computers inside of their facility. But the number of people who get hired to manage those systems isn't as big as you would think. There are a certain number of things that end up failing periodically. That's kind of expected. You don't have to replace everything when it fails. Maybe every month, whatever period, you replace things that failed, as long as you're within accepted tolerance. Failure of a certain number of things is just accepted as a cost of doing business, and it's cheaper to just replace things periodically and have a lot of redundancy than to have a lot of people who end up dealing with it. Also, there's a big approach of trying to avoid having operators. Why do you want to avoid having operators and having automated things, even if it means having more redundancy involved? Several reasons. Number one, operators are expensive.
Humans are slow.
Number two, operators make mistakes. There was a study made by the same Jim Gray I've already mentioned several times when he and I were both at Tandem. He looked at Tandem problem reports, TPRs. Tandem had systems that were called non-stop, a trademark. Non-stop was, the reference to Tandem being able to survive more failures than many other systems could. On the other hand, we had to deal with the bugs when something failed, hardware or software or otherwise. So internally we referred to Tandem as seldom stop systems rather than non-stop systems. It was pretty darn good for the time, but there would be bugs. And the analysis that he did, and he even published a report on this that was public, said that approximately half of the failures were due to operator error. So avoiding operators not only saves you money, it avoids many types of problems. Okay, so as of 2018, data volume was set to grow 800% over the next 5 years, and about 80% of that data, I said that it's more than 50% unstructured not in databases, 80%, but still in some kind of data management system. 80% of it would be unstructured, according to Gartner, which is, you know, probably the best known of the analysts that are out there. And another analyst firm, IDC, estimates that by 2025, this 163 zettabytes. This, of course, is not counting the NSA. Okay, there are all sorts of things that are out there that can, you know, talk about what's happening with respect to data. And again, I'm repeating this point about zettabytes, which was one on the earlier slide. So what, again, is a relational database management system? Well, that's pretty easy. It's a system that manages relational databases. And there are a lot of different parts of the system. The way that I've always thought about it is, and it's a little more than this now, but there are two parts to a relational database management system. The upper half, which is a whole lot like language compiler of a specialized kind, and the lower half, which is a whole lot like an operating system. The upper half handles parsing of this language, SQL, structured query language, that we'll be discussing. It does this thing called optimization, which is if the query says what you want, not how to do it, somehow you have to translate it into how it actually gets done. That's the job of the query optimizer, which despite the name is looking for something darn good as opposed to the best. Then when it finds it, it generates an executable plan. It also handles aspects of security at that level. The lower half is like an operating system. You store things, you actually execute the plan that is specified. You deal with issues of scheduling, you deal with issues of concurrency control so that things don't trip over each other. And you deal with making sure that you get durability so that even if there's a failure, the things that you were told, this really did happen, it committed, you make sure that those things really did happen. As I told you, you do an update, other people can update the data further if they're allowed to. But even if there's a crash, the update that you did doesn't go away. It could be changed further, but it doesn't go away. And again, we'll talk more about asset properties as we go forward. And here's a picture. If you decide to take Computer Science 181, which is offered in the spring quarter, which I teach, number one, it ain't the same as this course at all. This is a course about how you use databases, the externals of databases. That's a systems course in which you also have to write a simple version, very simple version of a data management system. This is how you use databases, externals. That's what's going on behind the curtain, what the internals are of database management systems. And there are a whole lot of different pieces of the database system that get discussed in that course, both the language-related parts and the operating systems-related parts. I'm not going to try to go through this because, well, I spent spring quarter doing exactly that. But I will go through that if you decide to take the course next quarter. Again, big emphasis. Maybe you like this course, maybe you do well, maybe my bad jokes don't bother you too much. Everything except the bad jokes changes in 181. Because that is a systems course. The bad jokes are ubiquitous. On beyond zero. So as I mentioned, the great majority, like almost everything except the last couple of lectures in this course, will be related to the relational data model. And that's what this lecture, which of course has already been posted on Piazza, is going to be about. And as usual, our textbook, it indicates approximately what sections are discussed, but as usual, I do discuss things that aren't in the textbook. I don't discuss everything that's in the textbook. So, but I'm pointing you to the most relevant stuff. Everybody had a lab on Monday or Tuesday. The labs in this course are concentrated at the beginning of the week this quarter. And everybody should already have a Gradients ID, which you got help with. Not hard to get, but you presumably got help in getting one at your lab section. There will be a Gradients assignment posted fairly soon. There are 4 labs in this course. The first lab with my singular lack of imagination is called Lab 1. I posted Lab 1 today on Piazza, and I will be posting a notice telling you about Lab 1 after this class, but I did post the Lab 1 out there. And it's something which is a relatively simple lab. You actually won't be able to do it until next Monday, but you can start looking at it and thinking about it even now. It is due January 23rd, so you've got some time to be able to go ahead and do it. It is by far the easiest of the labs. Make sure that you submit the right stuff and that you submit it on time. It has to be submitted as a zip file on Canvas. So the Piazza announcement will be out there later on this afternoon about the lab. It involves creating 5 tables corresponding to a stock market application. It's a really, really oversimplified stock market application, but what do you want? It's an introductory database course. So you have to do a startup based on that. We will also be posting some data that you can play with and explaining how you load that data into the tables. That'll be discussed in your lab sections next week. You don't have to do anything with that data to be able to get the assignment right. But I strongly advise you to do it for 2 reasons. It helps check to see whether or not what you did was correct. And it's fun, and will help you with what you do later on in the course. But something that I will emphasize all the way through the course, testing, e.g. playing with loading the data that you're given. Testing can show the presence of bugs, but it can't prove the absence of bugs. So just because something works on one example, it doesn't prove that it's right. A fellow by the name of Edgar Dykstra said that. He's completely correct. When you find that there's an error by doing a test, you know that there's an error. When you find there's no error from doing a test, well, you know that there's no error on that test, but there could be on other tests. Okay. So Canvas is going to be used for lab submission and grading. Piazza is going to be used for question and answers and announcements and posting of lectures and all the rest of that stuff. And now, I'm sure that everybody in the class figured out the answers to all 5 of these questions, numbered from 0 to 4, at least I hope. And now we're going to quickly go over the answers, and you know, at one point or other, I may actually raise the screen and do a little bit of fast writing on the whiteboard, probably without turning off the PowerPoint display. So, question number 1. S is 1357, T is 2357. What are S union T and S intersect C? Somebody want to tell me what S union T is? Hand, name, answer. All through the class, it's hand, name, answer. Go ahead, hand, name, answer.
My name, Robert, for the S union T, 1, 2, 3, 5, 7.
Okay, and because it's a set, duplicates don't get really counted. We're just doing set theoretical stuff. So when we get to multi-sets, which we will, we would count the 3 and the 5 multiple times, but with sets, it's just 1, 2, 3, 5, 7. Let's go on to somebody else for intersection.
Alexis, S intersect T is 357.
357. Anybody disagree? 357 it is. Okay, that was an easy one. A set A is 1, 2, 3. A set B is UVWXY. How many different ways can you pick one from A and another from B? You want to pick pairs of values where the first comes from A and the second comes from B. Somebody want to propose an answer? Hand, name, answer. First is any of 1, 2, 3. Second is any of UVWXY.
3 choose 5. 2 times 5.
Okay. How many think it's under 15? How many think it's over 15? How many think it's 15? How many are taking the Fifth Amendment, which is not permitted? Abstention is the same. It's like a for loop. For everything in A, and then you have a for loop inside that. For everything in B, you take the A value and the B value. For all the 3 things in A, you're going to be looking, for all those 3 of those values, you're going to be looking at everything inside B. So for 1, you're gonna be looking at the 5 values of B. For 2, you're gonna be looking at the 5 values of B. For 3, you're gonna be looking at the same, all 5 values of B. Last time I looked, 5 plus 5 plus 5, 15. Boy, are we gonna be dealing with the consequences of this kind of stuff throughout the first several lectures and beyond. Make sure that's clear. 3 times 5. Plus A has 3 different things, and B has 5 different things. Okay, now we're gonna be dealing with the incomes of the Beatles. John makes 10, George 20, Ringo 30, Paul makes 40. What are the names of the employee or employees, if any, who make less than the average salary? Hand name, answer, go for it.
My name is Keith, and John and George make less than the average.
What is the average?
25,000.
Right, so you add up the salaries, you get 100K divided by 4, it's 25K, and it's either, it's John and George, but not Ringo and Paul. Okay, we're gonna do the next question by a vote. And we're gonna have 2 answers, just 2 here, 2 valued logic, which is also what we have in question 4. Question is, can there ever be an employee who makes more than every employee? If so, give an example, if not, explain why not. How many think that there can be an employee who makes more than all employees? How many think that they can't? Large majority of people say they can't. Why do you believe they can't?
I'm Brain, and because if this person makes the most out of all employees, he doesn't make more than himself.
Yeah, whatever the maximum salary is, that person doesn't make more than him or herself. So there never can be an employee who makes more than everybody. Remember this when we get to the Martians later in the term, and yes, we will get to the Martians later in the term.
Is it a tricky
Okay?
question? Yeah.
Tell you what, this is easy enough that I'm not gonna bother writing it. Everybody should be, in this course, should be totally familiar with it. P can be true or false, 2 valued logic. Q can be true or false. So there are 4 sets of things to consider. Again, 2 times 2. When P is true and Q is true, when P is true and Q is false, when P is false and Q is true, and when both of them are false. Somebody want to tell me what the truth table is for the 4 things? Go for it.
As Kevin, and returns true when both P and Q are true at the same time and returns false otherwise.
Anybody disagree? That's right. And you should also know what OR is, and you should also know what not is. And if you found these problems difficult, you're gonna have a heck of a time in this course. But it's not a quiz, we're not collecting answers, just letting you know that all of these things show up in more complicated forms later in the course. Okay, what's a data model? It consists of 3 things. Kind of like an abstract data type. You've got the structure of the data, how the data is represented at some level, abstractly. You've got the operations that you can perform on the data. And you've got the rules of the road, constraints on what the data can be. We've talked about a number of different data models. I repeated those at the beginning today. So you know about a whole bunch of different sorts of models. And the relational model, which is from TEDCOD, okay, you have the mathematical concept of a relation, which you've probably learned about in a discrete math course. What is a relation? It's a structure that has a bunch of rows in it, which sometimes are referred to in database as tuples. I will be using row and tuple synonymously. And there are also columns, which are sometimes called attributes or fields, and you'll see examples of this. This particular textbook uses the term attribute to be the name of a column. Some others use it differently. When Codd defined the relational model, he liked sets. He didn't want duplicates. He hated duplicates. And when you store relations in tables and databases, there typically aren't duplicates because there are keys that uniquely identify, like a student ID. But SQL actually does allow duplicates during processing. Can anybody give me a reason why duplicates matter?
My name's Pete, and I can Think it would make concurrency controls a lot easier to process?
That's, then logically, might be multiple copies, but what I'm saying is not just actually inside something that you're dealing with. You care about whether or not value 10 appears once or the value 10 appears 12 times, and it's different. And I'll just briefly give an answer. We'll talk about this later. Suppose that what I wanted to do was to figure out the average price of stocks on the New York Stock Exchange. So all I care about is the price column, and I look at the prices of the stocks on the New York Stock Exchange. Does the average change if there's one stock value at 10 versus having 12 whose value is 10? Absolutely. The average isn't the same if there's one stock at 10. If I say, well, there are 12 stocks at 10, I'm just going to keep one 10 around. That changes what the average is. So duplicates actually can end up changing the values that you're playing with when you're doing calculations like sum or average or something like that. And now, we're putting Descartes before the horse. We're looking at Cartesian, we're going to be looking at Cartesian products. So a relation is a structure that has rows and columns. And the math sounds kind of funny, but it's going to be easy when you look at it. It's going to be something where you have these attributes where there are domains or data types from which the values come. For example, we might have a two attribute relation where the first value has to be A, B, C, or D, and the second attribute is restricted, so it can only be 1, 2, 3. And the question is, what is the Cartesian product of A, B, C, D, and 1, 2, 3? And in this case, I'm going to show you, but you should know, well, before we do it, anybody want to tell me how many things there are in the Cartesian product where the first value has to come from A, B, C, D, and the second value from 1, 2, 3?
I'm Brain, and I think the answer is 12.
Anybody think it's not 12? Anybody have a different answer? It's exactly like the previous example we looked at. I told you that was going to show up, and you didn't have to wait very long, did you? So it's going to be 12 because, well, right, for A, you can have 1, 2, 3. For B, you can have 1, 2, 3. For C, you can have 1, 2, 3. For D, you can have 1, 2, 3. Again, like this nested for loops, a for loop within a for loop. 4 times 3, which is 12. Okay? What are some examples of relations that come from that Cartesian product? Suppose that we have a rule of the road, a constraint on a relation, that the first value has to be A, B, C, or D, and the second value has to be 1, 2, or 3. Okay? And to say that you've got a relation where the domain of the first attribute is A, B, C, D, and the domain of the second attribute is 1, 2, 3, is to say that you've got something which is a subset of the full Cartesian product. Any subset will do. All 12 tuples? That's okay. No tuples? Well, that's not especially interesting, but that's okay. I could take the first 3 values, A1, A2, A3, and then D2. So I've got 4 things inside my relation. That's okay too. For every single one of the values, it's either in or it's out. And any way of doing that, any subset where you have the first value being A, B, C, D, and the second value being 1, 2, 3, that's okay. Any subset of the set that's written there would be a legal relation where the domain of the first attribute is A, B, C, D, the domain of the second attribute is 1, 2, 3. Here's another example. If the domain of the first attribute is A being 1, 2, 3, and the second is D, E, F, G, then the Cartesian product, which you write as A x B, the product of A and B, Cartesian product of A and B, would again be 12. 3 times 4 is 12. It's exactly those 12 things. So a relation that you have with domain A, the for the first attribute and domain B for the second, any subset of the thing that's written there. And again, just so you can see where the 12 comes from, we're, matching things where the first comes from 1, 2, 3, the second comes from CDF. Anything that you've drawn a line between is okay. It can be inside that relation if the data type or domain for the first attribute A is 1, 2, 3, and for the second B, it's D, E, F, G. Of course, I'm not going to stop there. I like for loops. Suppose that C is X1. What would A cross B cross C be? First of all, how many things are there in A cross B cross C?
24.
Please don't yell. Hand name answer, I'll call on somebody. You already answered. I was trying to have a question, I was looking for somebody else. How many things are there in A cross B cross C? Basically says the first thing has to come from A, the second from B, the third from C.
Diego, 24.
How many disagree with 24? How many agree with 24? Lots of people still taking the fifth or abstaining. It is 24. Because think about it, for every value of A, for every value of B, you can pick, you again go through for every value of C. For the 12 things that I wrote up there, they can be finished off with either X or Y. Or everything over there can be finished off with either X or Y. 12 plus 12 is 24. 3 times 4 times 2. So the Cartesian product of A, B, and C is going to be exactly what I wrote there, finishing up with an X or a Y. And one thing that we'll be talking about later, but I'll observe for you right now, is I didn't put parentheses around this because it doesn't matter how the parentheses get put in. A cross B and then cross C is going to be the same as if I take A cross the product of B and C. Much like multiplication or addition, but unlike subtraction. Subtraction, the parentheses matter. Product, like multiplication and addition, is associative. Okay, tuples. Come to say tuple. What's a k-tuple? A k-tuple is a sequence, ordered sequence, order matters, of values. It has to be k values, which is why it's a k-tuple. Okay? The values don't have to be different from each other because there are k positions and the same value might appear in more than one of those positions. And so 1, 2 is a binary tuple, or this is fun to say also, a two-tuple. So 1, 2 is a two-tuple. A, B, B, even though there are 2 B's there, that's a ternary or 3-tuple. Of course, there's an A in the first position, a B in the second, also a B in the third. 1, 2, 2, and CS, F, I think there's an extra quote over there after the F, I'll get rid of that. F and 3.95, that's a 5-tuple, 5 values in it. Don't know how that extra quote got in there, I'll have to fix that. Now we'll generalize mathematically, now that you entirely understand about k-tuples. If D1, D2, up to dk are sets of elements, like our ABC, 1, 2, 3, 4, U, V, W, X, Y, and so on. If D1 through dk are sets of elements, the Cartesian product, which again, you don't have to have parentheses for,